So to finish up this number theory section, I want to give you two lemmas and a theorem. And basically the first lemma is going to be the integral part of the theorem, and the second lemma is more just to apply the first lemma. So this lemma, lemma 2, is really going to be the key to this segment. So lemma 2 says, for any natural numbers a, b, and c with the GCD of a and b equal to 1 and a dividing b and c, that means that a divides c. The basic idea is if a divides b and c, b times c, and a doesn't divide b, that is, a is co-prime to b, then all of a's factors must have lived in c. So that is a divides c. All right, let's prove this lemma. Now it's a bit of a proof. So what I'm going to do is I'm going to have to sort of go through and do a few different steps. So this is going to be not a super complicated proof, but it is going to be a slightly complicated proof. So since a divides bc, we know that there exists an integer k such that bc equals ak. All right. Next, so let's remember this. Next, by theorem 6, that is the Bezier identity, we have that the GCD of a and b equals 1 implies there exist s and t integers such that sa plus tb equals 1. That's the GCD of a and b. Now, I'm going to multiply both sides of this equation by c, and I get SAC plus TBC equals c. But I know something about BC. It equals AK. This tells me that SAC plus TAK equals c. But look what I can do. I can factor an a out, and I get a times SC plus TK equals c. But this is an integer, which means that I can write c as a times an integer. And if I can write c as a times an integer, that means a divides c as claimed. And that's the end of the proof. Now, this isn't that complicated of a proof, but I think it's worth pointing out that we had to kind of do two things. So oftentimes with our proofs, before this point, we've just sort of unfolded a definition and rolled down a hill, right? So, like with the proofs in this section, we sort of, I'm going way back to the start here, like these, we just sort of unfold this definition, and then we roll down a hill, consider the quantity. Okay, so now what we're doing is considerably more sophisticated. In this section, we've had this, we've had this proof that relied on some earlier exercises. We had this proof that relied on using, proof by way of contradiction. So the proofs are getting a little bit more complicated. All right, let me give you lemma 3. And lemma 3 is really just going to be an application of lemma 2. So given a prime p, so this is a prime number, and integers aj, so this is, j is some index, so I've got a1, a2, a3, etc. up to, say, an, and aj is just saying, it's a generic name for all the integers. If p divides the product a1 times a2 times ... times an, then p divides aj for at least one of the aj. And all this is saying is if p divides the product of these numbers, then it has to divide at least one of them. And the proof, and I'm not going to give you the whole proof, but the proof is basically lemma 2 and the fact that the GCD of a prime with anything is a multiple of P. Is 1 or a multiple of P. Okay, so that's not the complete proof, but what we do is we'd apply lemma 2 to A1 and the rest. So if P divides A1, then we're done. If P doesn't divide A1, then we treat A1 as our B and the rest of this as our C. So that means P divides this product of A2 up to AN. And so then we try it again. And we peel off A2 and we say, okay, P either divides A2 or A3 through AN. If it divides A2, then we're done. If it doesn't, then we need to look at the rest. And we keep going and keep going and keep going until we are done. Now, to make that process more formal, we're going to learn something called mathematical induction. And that's something, so we'll be able to do a proof like this more formally. I just kind of wanted to sketch it for you now. So the next thing I want to do is Theorem 7. And this is going to be another application of lemma 2. So Theorem 7 says, given a natural number m, and integers a, b, and c, with the GCD of m and c equal to 1, if AC is congruent to BC mod m, then A is congruent to B mod m. Now, there's a pretty straightforward proof of this, but what I'm going to do instead of giving you a complete proof is I'm going to write down a little table to show you how to apply this lemma 2 to get a proof. So the basic idea is I'm going to set m from this proof is going to be A from lemma 2 I'm going to have C from this proof, or from this theorem, is going to be B from lemma 2. And I'm finally going to have A minus B from this proof is going to be C from lemma 2. So what am I doing? I'm saying I've got natural numbers, A minus B, C, and M, so natural numbers or integers, as the case may be. And really, if I've got an integer where up here I need a natural number, I can preserve my divisibility relations by just throwing in a minus sign. And what I've got is that the GCD of M and C are 1. So the GCD of these two, M and C, are 1. And these are M and C. These are A and B in lemma 2. They're M and C in my current proof. So if these two are coprime, then what's that mean? That means A divides B times some other quantity. Implies that A divides that other quantity. So what do we get? If M and C are coprime, then I'm saying M dividing C times the quantity A minus B is this, with these two coprime, is actually telling me M divides A minus B. So where do I get the M divides C minus, C times A minus B? Well, we know that M divides C times A minus B because this is precisely AC is congruent to BC mod M. All right, so this tells me this, and I am literally just applying lemma 2 with a few different values. Now, and this gives me the conclusion, which is C divides A minus B, because C divides which is M divides A minus B, because M divides A minus B is precisely what I wanted to prove. So again, like I said, this is just kind of a sketch of the proof, but I wanted you to see how we apply lemma 2 in a different proof. Okay, the last thing I want to do is give you an example of when this doesn't work. Okay, so I've given you an example, or I've proved this theorem, but I want to give you an example of when it doesn't work, because I've been leading up to this for a while. I've said, this triple equals is a lot like an equal sign. So if I have AC equals BC, then I can divide both sides by C and I get A equals B, right? But that doesn't always happen. What this theorem says is, well, even though that doesn't always happen, if M and C are co-prime, then when I have AC congruent to BC mod M, I can sort of cancel that C off. I can cancel this C because they're co-prime. So let's see an example of when I can't cancel that C. Here's my example. That is 3 times 5 is congruent to 3 times 7 mod 6. So we can check this. 3 times 5 is 15, which is congruent to 3 mod 6. 3 times 7 is 21, which is also congruent to 3 mod 6. But I can't just cancel these 3's off of both sides, because we notice that 5 is not congruent to 7 mod 6. Okay, and the reason this broke down is because the GCD of 3 and 6 is not 1, right? The GCD of 3 and 6 is 3. 3 divides 6, in fact. So that concludes our discussion of number theory. This proof, if it doesn't totally make sense, that's kind of okay. I gave you a pretty quick treatment of it. But if you look in the notes, you'll see not only this proof, but also another proof that essentially follows this argument through line by line. If you go through that proof, then I think you'll start to see how the quantities line up, and that'll make this proof make a little bit more sense. But that's really just repeating what we've already seen, so I'd rather you look at the notes and go through that.